But then, as Feynman said, nearly anything is interesting if you go into deeply enough. Filipinos have the capacity to embark on these kinds of studies and have a voice in this international collaborations. Lots of things that we have to discover and study. I am Tristram Acuna, so you can call me Tram. And currently, I'm a Ph.D. student here at the International School for Advanced Studies in Trieste, Italy. Yeah, I'm affiliated with the Astroparticle section, and also I am affiliated with the Institute for Fundamental Physics of the Universe. So actually, before coming here, my research interest is in gravitational physics and classical general relativity. I had plans of working with this particular professor, but then I had been made aware that there are other students working with a professor, and professors can only handle so much. I decided to make the switch, and it was actually a risky move because it's like shifting to a field that I wasn't initially interested in. But then, as Feynman said, nearly anything is interesting if you go into deeply enough. Okay, so I said, okay, I'll work on this dark matter project. And of course, at the start, everything was not going so well. It's really frustrating, and your code doesn't work. But slowly, you see, okay, things are interesting. Things are working, and then eventually, that led to a paper. And yeah, so I have learned how to, love this field, and I have really appreciated how this field has developed, and how can we contribute to this field. It's a good opportunity for me to at least say a few things about dark matter. So dark matter is a form of matter that we know interacts only gravitationally, and we have accumulated tons of evidences pointing to its existence. And our present knowledge of cosmology tells us that most of the matter content in the universe consists of dark matter. Just from a historical perspective, dark matter was introduced to address certain issues regarding missing mass, and it was pointed out by Fritz Zwicky and others when they realized that there is more matter residing in galaxy clusters compared to what we inferred from optical observations. The point is, we know that dark matter exists, but frustratingly, we don't know what it is made of. We're pretty sure it's not some particle in the standard model, because we know that dark matter cannot interact by electromagnetism because we don't see it. Right? So my work essentially involves exploring possibilities as to what dark matter is. And typically, so if you go back 3 decades ago, there's this proposal of the WIMP dark matter. So it's like a single dark matter candidate. But in one of my projects, we considered this multi-component dark sector. So it's like a framework wherein you have multiple stable dark species. We studied this particular realization of a multi-component dark sector. And like in this case, there is this sort of dark force that exists between these species. And in quantum physics, when you have a force, you should have a mediator. Like for instance, electromagnetism is mediated by the photon, and the electric interactions are mediated by the W and Z bosons. In this case, the interaction between the dark species is mediated by the dark photon. It's an oxymoron, right? Because it's a photon, but it's dark. But the point is, it's like a kind of force that only exists within the dark sector. But then there's a problem because like dark photons in this case are massless, so they contribute to the radiation component of the universe, and that would affect the expansion rate of the universe. And so the question is, okay, given what we know about the expansion history of the universe, what constraints can we put on the amount of dark photons that we can have in the dark sector. And by doing so, we were able to actually obtain bounds on the possible masses of the species in the dark sector. The strongest motivation for exploring multi-component dark sectors is the fact that you have more dark matter in the universe than visible matter. And the visible matter can be described by the standard model. And the standard model is something that has some intricate structure. First of all, we know that the standard model describes, most of the matter that we see, right? I mean, it's an elegant theory, but then there are issues within the standard model. And I think that the most obvious one is the fact that it predicts zero mass for neutrinos. So at least if you know what a neutrino is, it's a lepton. It's like it's a partner of the electron, the mu1 and the tau. But then we have these experiments, neutrino oscillation experiments done in the late 90s that point out that neutrinos have mass. Okay. So then that's one obvious signal that there must be something in the standard model that we have to modify. We don't actually know what the mass of the neutrino is. We only have bounds. And you have these bounds coming from terrestrial observations, you have bounds from cosmology, and so on. So the point is, like, the current issues in the standard model is actually driving most of the research to explore theories beyond the standard model. It's an elegant theory, but it's a bit complex. And so why would you expect that dark matter, which comprises 26% of the energy budget of the universe, is described by just one candidate? So we explore like this complex possibility, and like we have found implications in cosmology and direct detection prospects. So like that's just the general idea of the interesting result that I got from one of my projects. So I'm aware of the existence of various initiatives to promote space science in the Philippines. So back when I was there, I've been to the Mine Museum, they have public talks and so on. And then you have SEDSPH, right? It's one of the initiatives, right, to promote space science. And also there's the Philippine Space Agency, right? And we have also sent microsatellites in space, and we have found various applications of that. For instance, monitoring vegetation, ensuring national security, and so on. And given this, if we keep this steady pace, and assuming that government support would still be there, I would say that the future is bright for space science in the Philippines. And okay, so at least I have my own visions for space science. And okay, well, at least as a dark matter phenomenologist and as an astroparticle physicist, so at least I'm not really much into space exploration, like going to Mars or so on, or going to the moon. But in my opinion, I think that Filipinos can dream on and think about carrying out space exploration in the context of performing investigations in basic science. So it's not really about developing our own technology, but rather we can perhaps forge collaborations with research groups carrying out these kinds of things. And in the context of astroparticle physics, there are several future missions whose aim is to obtain a better understanding of the universe. You have the LISA, the gravitational wave mission. You have LIGHTBIRD, which aims to perform more precise measurements of the cosmic microwave background anisotropy. And so it's one of my visions. Like, Filipinos have the capacity to embark on these kinds of studies and have a voice in these international collaborations. But of course, in order to participate in these endeavors, we have to improve our educational system. We have to admit that there are issues in the educational system. So So at least we have identified like those issues, we have addressed them, and hopefully we can do more.